this is Cody Jackson for Codemom, and we are continuing our Python journey by talking about Python files and input-output operations. There's one section in the book that I'm not going to be including in this video because it's not really relevant. It's about seeking within files. So if you want that information, you can either look on the internet, or if you have the book, just take a look at that chapter and you'll see how to seek within a file. So, Python input-output operations, typically involving files, which is what we're going to talk about here, but obviously you can also have input-output on network streams and things like that. But we're exclusively going to talk about file operations in this video. Python uses the operating system file system structure to actually perform operations. So the file system has its own way of accessing data files, and that's dependent upon the operating system. But Python has a file access API, which allows Python to be cross-platform. So as long as there's a Python interpreter available for your operating system, Python knows how to deal with that operating system and perform file access. If you don't recall, an API is an application programming interface, and it's basically a black box where all you need to know is what goes into it and what to expect out of it, and the actual functionality is irrelevant to you. So to create a file, all you need to do is tell Python, hey, here's the file name, open the file, and then write to it or read from it, as the case may be. There's a number of file access modes that are available when working with files. You have read-only access. This is the default access mode when opening files, and this is to ensure that you don't accidentally overwrite data. If the file does not exist and you're trying to read from it, you're going to get an error because obviously there's nothing to read from. If you have an R+, then that opens it in read-write mode, and again, if the file does not exist, an error is going to be generated. You can have a W to write to the file, and that will overwrite any existing data. If the file does not exist, because you're opening a file to write to, it will create that file for you and an error will not be created. W+, similar to R+, is read-write mode. Like a write file, it will overwrite any existing data, and if the file doesn't exist, it will create a new one for you. A allows you to append to a file and read. In this case, it does not overwrite the data, it simply adds it to the end and keeps extending that file. And like write mode, if the file doesn't exist, a new one will be created. And then basically if you add a B to any of those modes that we've already talked about, that means that you are going to open the file in binary mode, which means that the data that is stored in the file is expected to be non-textual. This is only necessary on Windows and Mac. Unix platforms don't care about your data type. However, unless you know you're exclusively going to be using this data on a Unix-like operating system, it's safest just to use binary mode just to make sure that you don't break anything. Buffer control. I don't recall if we've talked about buffers before, but a buffer is basically just a chunk of memory that is used to temporarily store data before it is processed in some fashion. Because a buffer is normally used for file access, it's not even thought of when working with files. So you provide the file name, the access type, and you just tell the computer open log text in write mode. There is a third argument that you can provide if you want to, and that third argument controls how that data buffer is going to be used. So if you use a 0 as the data buffer argument, then it means that you do not want your data to be buffered. It is going to be directly written to that file. And as noted, this is only available in binary mode. If you use a 1, then you are telling it to use line buffering, so line by line is going to be stored in that buffer and then written to the file. This is only usable in text mode. And if you use a value greater than 1, then that indicates the size of the particular buffer size. So in terms of how many bytes that buffer is going to be able to hold per operation. And if you don't put anything, then Python uses a default value, which basically just says create a buffer as big as I need for these file operations. So those are the access modes. We are now going to talk about the different operations that you can do with files. So you can create a file for writing, so an output. You can create a file for reading, input. You can append to an existing file, output again. You can read the entire file into a single string, and this is dependent on the amount of memory that you have. You can read a certain number of bytes per read operation. You can iterate over the lines, so using a read line or read lines, and that would basically iterate line by line through the file. And one is purely just reading the lines as text strings, and then read lines creates a list of each of those lines from the file. And then you can write something, in this case some string, to the file. So basically whatever you have within the parentheses is going to be written to that file. Or if you have a list, you can use write lines, similar to read lines, and it's going to write that list of strings to the file. And then you have close, which manually closes the file. Now, regarding closing of files, Python has a garbage collector, so you don't really have to manually close files like you do in other programming languages. Once that file is no longer used and the garbage collector comes around and sees that it is no longer referenced, it will close that file and remove all references to it from memory. However, it is good practice to manually close files, because there are times when you may be using a different Python environment that doesn't directly support garbage collection, or the operating system itself may have a dysfunctional ability to work with Python files and not close them correctly, resulting in memory leaks. If you want to keep a file open for use without closing it after every operation, you can use the flush method to flush the buffer, write all of that data to the file while keeping the file open. So normally you would open the file, do something with it, close it, open it, do something with it, close it. But in this case, you can open it, do something with it, flush the buffer, do something with it, flush the buffer, do something with it, close it, and closing will flush the buffer and close that file. Data streams. So in the Unix world, everything is a data stream. So files are not a discrete object. It is a structure of text strings or binary data streams. And so these streams can be used in a variety of ways. So each file has an end of file marker at that last byte, and that's basically what tells Python when to stop processing it. So when you open a file, you basically open the floodgates and allow this stream of data to flow through for processing until that end of file marker is hit, and then it says, all right, you're done, nothing more to process. And because of that streaming nature of the files, you can read the entire file all at once, read it line by line, read a certain chunk of bytes per time. It doesn't matter to the system. It all depends on how you, as the developer, want to deal with that file information. Now, we already talked about, depending on the file size, if you try to read the entire file at once, you may exceed the amount of memory that's available for that data stream. And therefore, processing it line by line or in chunks of bytes is more common, just to ensure that the memory that's available is not overloaded and you have errors. Data serialization is the process of using binary data, so data structures like lists, dictionaries, classes, things like that, within a file or a network data stream. So Python normally expects files to be textual, but as we saw, you can use the B at mode to tell it to use binary data. So there are two types of serialization to use, pickle and shelf. Pickle is more common simply because it's a little bit more versatile. It converts your non-textual binary data to byte sets or byte codes that can be stored or transmitted over a network. So stored into a file or sent over a network to another computer for further processing or writing to a network file. And that requires the B access mode. Shelving is similar to pickling. As a matter of fact, pickle is used on the back end of shelf to handle the data serialization, but the primary difference is that shelf functions more like a dictionary where you are accessing the values of your data based on a key that's provided. And basically you get a simulated database this way. So the values that can be used and assigned to a key is pretty much any sort of data structure that Python has. So class instances, recursive data types, pretty much anything really. So you either just pickle the entire information data set and either dump it to a file or you send it over the network, or you use shelve to be able to access that binary data via a keyword. And it is important to note that there is no inherent security for serialized data. So unless you are creating a pickle object and sending it and then manipulating it yourself, if you are taking data from some other location and you can't verify it, you can't authenticate it, you basically know nothing about it, don't touch it. It's the same as putting a website up there and not having any sort of data validation, and so people can put anything in there and start gaining access to your web server. All right, so that's enough of the academic theory of files. Let's actually look at how files are used. So in this case, I've created a new file. The variable to work with a file is called this file. The file name itself, i.e. what you would see on the file system if you're looking in File Explorer, would be a file.txt. We open this file with W, meaning that we want to write to the file. And then in the next line, line 4, we actually write the sentence string, "Hello darkness, my old friend." Now, Python in this newer versions, Python 3, will tell you how many bytes were processed into that file, in this case 28. Then we manually close it in line 5. In line 6, we open the file but give it a different variable for access, just to show that what we are working with is not tied specifically to that file name as seen by the file system. In line 7, we see that we can do a read line of that file, and it returns the data that was written to the file. In line 8, if we do a read line again, we get an empty string back, and that empty string is actually the end of file marker that we have received from the file access. Because if we try it again, we're going to get it again, and that's going to happen every single time because there's no more data to read. If you want to read that data, you would have to reopen it again. As we show in line 10 and line 11, we reopen it, that data is available again to the stream, and so we do the read line, we pull that data out, and then that stream is basically automatically closed because there's nothing more to access for that particular data file stream. So to write to a file, we open the file like we did previously, and you either use the W mode or the A mode. In this case, we're using the A mode for appending, so we can write multiple information to the file without overwriting what is present. Lines 14 through 16 are just adding new lines to the file, and you can see how many bytes were taken up by that. And then in line 17, we manually close the file again. Line 18, we open the file for reading, and line 19, we use the read line method, and it prints everything in the file. Now, that may be counterintuitive because you said read line rather than read lines, and you would think that that would just be a single line at a time rather than all of the lines. But we did not tell Python to put line markers in there. In other words, a new line character was never put after each of those lines. Therefore, while we were writing them as separate lines, for Python to append them to the file, it was adding them all as one line because there was nothing to designate that there were different lines. I don't think I've talked about how IPython works directly in terms of tab completion. When you are working with IPython as an interactive interpreter, you have the ability to do tab completion, and based off of what is going on, it will give you the potentially correct methods, function calls, things like that that you want to use. So if I want to access a new file called add file, and I put a dot, and then I can look through here and use a tab, and that will show me all of the items that are available to be used for this particular function call. So add file, it knows as a file. We've already opened it up in line 20, and then it's giving me everything that can be used for file operations. You have different methods in here like flush, read, things like that. And I wasn't paying attention, and I just used this, and you can highlight what you want to use, and it tells you writable is a function, write is a function that takes a text argument. So I just went ahead and highlighted writable without paying attention when I wanted write. And because I did that up in line 21, that's why it gave me an error. Writable does not take an argument, but I gave it a text string argument. So if we do it correctly, then we should get the correct output. Moving on, we have added 3 new lines to the file, and they all have the new line character at the end of those lines. We've closed the file, we reopened it, and you can see because we appended, we have the original text here, all of these lines put together. Here is the new line, and you'll see that it stops at that new line character. So it's not all of these extra lines added together like it was the first example. We actually have it stopping at the new line character. But it is showing us that new line character, which can be bad, but it's also good because you know that it's working. If we use the read lines method rather than read line singular, you'll see that it is taking the rest of the lines in the file, giving those all to us, but as a list of text strings. So our first object within the list is a text string, and then we have our comma as usual, and then we have the last item in the file, which is the final string that we have put in there, and it's all wrapped up as a list. So you can dump everything as a list of strings and then process those as a regular list, iterating over the list, processing it, things like that. So if you want to see what would actually be used in a user-friendly way, rather than the raw text with the new line character, you have to use the print function to process the file. So in line 29, we open the file again. In line 30, we print read file. So that's just print to us the information of that read file variable. That obviously the variable can be anything. So this shows you a couple of interesting things. Now I'll admit I screwed up. I forgot to add the read, which we add down here in line 31. But it does allow me to show a couple of things. First off, it shows you that read file as a variable of an object. It's an IO object, and it is a textual wrapper, IO wrapper, around that IO object. Gives you the name of the file that the variable is referencing, and it tells you that it was written in read-only mode, and it tells you that it's in UTF-8, which is basically Unicode. In line 31, we actually read the file and print it out, and you can see that everything is sent as it was up here, just without the new line characters. And so this is how you would see it. Another thing is that here, when we did a read lines, we got a list of strings. When it is printed, Python is intelligent enough to separate the lines into actual new lines. So it sees the new line character, jumps to the next line, and prints the next object. So one thing to note is when you are working with files and you know that there's the potential of getting an exception, which we talked about how if the file is in read mode and that file doesn't exist, you'll get an exception, then you can go ahead and create a try and except block to deal with that potential exception. This is an example of what I'm talking about. So we wrap our open, read, print, close statements all within a try block up here. And then we have an exception. If we receive an operating system error exception, then print to the user the file doesn't exist. If we do it on new file, which we just used, we know that we should be expecting the regular output. If we do it with a non-existent file, in this case no file, then it tells us the file doesn't exist, as we expected. If we did not capture that exception and we just let the error propagate as normal, we caught it a little bit in this instance. So in 35, we, instead of making a pretty print message to the user, we just capture the error as variable E, which is kind of a standardized practice for capturing errors that you still want to do something with. And then we print E, which is the error message. Then we see that the error that comes back is no such file, no file.txt. If we did not do that at all, then we get a really ugly error message of basically the normal stack trace that's going to be coming back. So it's going to tell you file not found error, the trace back that you would be getting, the file that's causing it, and the particular line, and then it gives you the normal file not found error, and then that error itself. So one thing to note, we talked about it when we were talked about exceptions, is the hierarchy of errors. So file not found error is a subset of OS error. So while you can specifically look for file not found error, which is actually better, if you don't know exactly what error is going to be coming back, then you can move up the hierarchy, and you know that OS error pretty much handles a large number of exceptions. And if you don't want to deal with each one of those exceptions, so if you had a file not found error or file corrupted, whatever the case may be, just use OS error to capture anything involving file operations and deal with it that way. Or if you want a specific error message or some sort of logic to go do something else in case a particular exception is thrown, then you can use those more specific exceptions. The best practice when working with files, either reading or writing to them, is to avoid manually closing the file. If you use a with object as file name variable, then Python will only keep that file open as long as necessary and then will automatically close it. So as we see in this example in line 38, with open file name as a variable name, a file, work with it in whatever fashion, in this case print it to the screen, and because it's a with loop, basically with this object opened as a file, when it is no longer being used, it's automatically going to close. And I think I said with loop. With is not a loop. I was thinking the while loop. So this basically is just, as long as this file is being used for processing, I'm going to keep it open, and then when that is no longer used, I'm going to automatically close it. So this is similar to garbage collection, but puts a little bit of a manual twist to that garbage collection. This is actually the preferred way of dealing with files, just to make sure that you don't have any files that are inadvertently open, taking up space, causing memory leaks, and otherwise ruining your life as a programmer. We talked a little bit about iterating through files using lines. So if you just use a standard for loop, it handles a lot of it for you. So in example, line 40 for here, for line in, open our file, print that line, and then it's just going to iterate through that file, printing each line as it sees new line characters, and then automatically close the file. So same thing that we did previously, except we're using an iterator to handle it rather than doing a with file open. You'll note that there's an extra line space in between each line, and that's just by virtue of how the print function handles printing. It automatically defaults to adding a new line character itself. So if you don't want to do that when you're working with this, then you just tell the print function to use the ending character is going to be nothing. And that eliminates the print function's new line character, but still keeps the new line character that you put into the file. Finally, we're going to talk about serialization, specifically the pickle module. In line 43, we import the pickle module. We create a list of integers. We open a file called pickle file, and we specify that it's going to be binary, so a WB. In line 46, we dump the list that we created to the file that we created in line 45, and then we close that file. If we take a look at our file system, we can see that we have a new pickle file here, and it's showing us that it is a binary file. If we try to open it, it has no clue what it is. Now, assuming we had saved that file and wanted to open it later, or we sent that file to someone else, just as a file transfer, something like that, we can open that pickled file using RB, specifying that we want to use binary mode while reading the file. We create a variable, unpickle, and we open the pickled file using pickle.load, giving it the file open list, and then we can print what has been unpickled, and it gives us that list back. So in this case, what we have done is we have created a data structure, a list, from Python, wrote it to a file, did something with that file, reopened that file, and we're able to access that data structure that we would not normally be able to work with. And that's the power of data serialization, is that it basically means that you can take source code, and while your source code is going to be in a textual fashion, if you wanted to process your source code and actually create objects and work with those objects in a different fashion, so it's not pure source code, and you're basically creating a binary object, and you're going to pickle it to be sent over a network to another computer, say a server for processing and stuff like that. This is where your pickle data serialization comes in. I'm not going to cover shelves because it's basically the same thing as pickling, except that you are effectively creating dictionaries of your data rather than just purely doing the data. If you want more information, you can look it up online. You look at it in my book. But honestly, I can't think of a time when I have seen a shelf being used. I've seen pickle more often being used. So that's it for this video. We talked about how file operations are universal via the Python API. The file access mode dictates what a user or process can do with a file. Read only, write, append, working with binary files. Your file operations are how to actually work with that data. Read a single line, read a list of lines, whatever the case may be. Manually closing is best practice. You can use flushing if you want to keep the file open for further processing. We talked about how you can use the with open file as variable name as a way to manually / programmatically close your file when you're done with it, so that you don't have to think about manually closing it. We talked about how files are just data streams, and therefore they can be processed in a number of ways. You can take a chunk of bytes and process that chunk, and then grab the next chunk and basically handle the chunks in a serial fashion. You can process a file line by line, whatever you want to do. And then finally, data serialization allows you to work with binary data just as if it was regular text strings, but it's a data structure within Python. Next time, we're going to talk about SQL data and basically start getting into how Python can be used to interact with databases. I hope you enjoyed this video. If you have any questions, comments, please let us know. Until next time, keep learning, have fun, and have a good life. Bye.